A person with a mass of 80 kilograms standing on a frictionless horizontal ice surface, and throws a 0.25 kilogram ball in the horizontal direction. After throwing the ball, the person observed to be sliding backwards with a speed of 0.4 meters per second, 0.04 meters per second, with respect to the ice. What is the velocity of the ball, the horizontal component of the speed of the ball with respect to the ice? Okay. So this is going to be a conservation of momentum problem. So we have, I guess we should first draw a picture. So ice, person. That's a terrible, I don't even know what I was trying to draw there. Ball goes that way, person goes that way. So we have a conservation of momentum where, and we'll say this is, so we have P1, 2? Yeah, I'm going to say P1, 2, because they're together to start with. And that's going to equal the final, which will be P1 plus P2. And I can put finals here, but we know that the only time that they're separated is after the fact. So I'm going to leave it like so. Click, click. So they're initially at rest. Massive kilo, standing still, right here. It's funny how they always come up with different words to say the same thing. So standing still, at rest. So this is, I'm going to write this as mass 1, 2, V1, 2, because that's momentum, equals mass 1, V1 plus mass 2, V2. V1, 2 initially equals 0, because that's the combined person-ball system. And then we have mass 1, V1, mass 2, V2, and this will equal 0 over there. Now, these velocities are opposite, so what I'm going to do is I'm just going to kind of move them over to the opposite sides. M1, V1 equals M2, V2. Now, in reality, this is going to be negative V2, but I've already left off the little vector symbol, so it doesn't. I'm going to use common sense here and just ignore the signs. Sometimes you can get away with that, especially when you're crunched for time. If you get too bogged down into the details of minutia, then you never actually get anywhere. Or you get somewhere so slowly that it doesn't matter. Okay, so we're looking for V ball. I'm going to call ball number 2. So V2 equals mass 1 V1 over mass 2, which equals 80 times 0.04 all over mass 2, which is 0.25. And you can see this is basically just a ratio based on the masses multiplied by the velocity. So we take this on clear, clickety-clack, 80 times 0.04 divided by 0.25. I could probably do some of that in my head. 12.8 meters per second. See what our possible answers are. And 13. We'll go with 13. 13 seems reasonable. So looking at these answers too, there's if you're strapped for time, and if you're taking this for a test, you're of course strapped for time. And these kind of questions, you're only really given like 2, maybe 3 minutes. Probably closer to 2 minutes. So you don't have a lot of time to work on these. So just looking at the possible answers here, they have this one, which is basically, so start with this one. This says that the ball leaves his hand at the same speed that he does. We know from the idea of conservation of momentum that's not true. We're going to have a slow-moving, heavy object, and from a momentum point of view, that'll be the same as a fast-moving, light object. So we know it's going to be fast-moving compared to this guy right here, which we're already told is moving at 0.04, so we want a number bigger than 0.04. So it's not going to be 0.04. 1.2 times 10 to the -4th, smaller than 0.04, therefore not true as well. And we can basically look at these and be like, all right, A and B, not possible, therefore it's going to be C. Process of elimination. I'd still recommend going through the problems as much as you can when you have time, but when you don't have time, take as many shortcuts as possible. What is the magnitude of the average horizontal force by the hand on the ball, assuming it took 0.15 seconds to accelerate the ball from rest to its final speed? So let's see here. I think they said average. Average, that's important. So let's see here. I think force equals dp dt. And you're thinking like, wow, how did you find that random equation? I think this is the definition of momentum. I know that there's some sort of relationship between time and force and momentum. And the way I mnemonically tie this to the iceberg, I anchor it, so to speak, is I do dimensional analysis. You can almost pass Physics 1 solely through dimensional analysis. Just make sure all the units match up. You do get kind of a problem with things like kinetic energy and like energy of a spring, because you have that 1/2 in there. It's like, oh, off by 1/2. But for most things, it kind of works. So force is mass times acceleration. So you have kilograms, and acceleration is meters per second squared. That's an S. I'll redo the S for you. S. It's a cursive S. Momentum is kilograms times velocity, which is meters per second. And then T is seconds, so you divide by another T. This gives you kilograms meters per second squared. And they're both the same. And that's kind of how I remember that that's the way to do it. I know that they're all related, and the way I kind of figure out how to put them together is through dimensional analysis. So now that we have this magical formula that we pseudo-memorized, half mnemonic, we can use it to figure out what we need. So we have a dt here. So let's see here. Average horizontal. Okay. So if we say average, then what that's basically meaning here. So if we arrange this, f dt equals dp, integrate both sides. If you've taken calculus, this kind of makes sense. If you haven't taken calculus, then this is crazy talk. But we're going to go with it. Average is going to be a constant average force. So this isn't the force that's applied to the ball. This is the average over the period of time, 0.15 seconds. And so if it's an average, it's a constant, so we can pull this out. So we have f integral dt equals integral dp, which is momentum. And this dt here is just going to be a delta t, a difference in time. And this will be the change in momentum. So the change in momentum will be force times the change in time. So this is the equation we want. What is the magnitude of the average force? We're still looking for force on the ball, assuming it took 0.15 seconds to accelerate the ball from rest to its final speed. So we have force equals, I'm going to say mass times change in volume over change in time. I change in velocity, not volume, velocity. I'm going to say change in velocity and not change in mass, because if we did change in mass, we kind of have to do some other things. But we're going to look at it just in change of velocity, because I'm going to assume the mass, for the most part, stays the same. And we know its final speed from the previous problem, so we have 0.25 times 13, right up here, 13 milliseconds, divided by 0.15 seconds. Yeah, seems reasonable. All right, well, let's calculate that out. So I have I'll still go 12.8 times 0.25 divided by 0.15. Yes, 21.33. 21.3, and then there's a repeating there. And our possible answers are 0.067 or 21.3. So we're pretty sure it's not going to be 0, because there's going to have to be some force that you throw the ball with, otherwise it just won't move. I don't have a real strong conceptual understanding of what 0.067 newtons is. What you can basically convert it to mass. Force equals mass times gravity. And so if you have a force of we basically divide by gravity. Force times gravity would be an equivalent mass. Gravity is about 10, so you're talking about 0.006 kilograms, which is about 6 grams, which is like 6 paper clips. So this is basically saying that how hard you threw the ball, the quarter-kilogram ball, was basically 6 paper clips worth of average force over a sixth of a second, which, it does seem light. And then this one, which is the correct answer, that's the one we calculated out, and that's basically like, divide by 10, 2 kilograms. So it's like, yeah, 2 kilograms is pretty heavy. The same force required to hold up 2 kilograms is the same force that you threw the ball with. It's like, yeah, that seems about almost reasonable. Okay, so that's how I would approach this problem. It can be done pretty quickly just through looking at the answers and analyzing them. If you're extra arrogant and cocky and confident, maybe go for it. But this is I also showed the way that you would work through it in a more methodical manner. Hope that helped. See you next time.